Okay, so now let's go over Lewis structures. Lewis structures are the most powerful tool that we have for being able to conceptualize what a molecule looks like and, damn it, and how it's going to behave. So, some notes. Hydrogen is always the terminal atom. Hydrogen will only ever form one bond. So if you only form one bond, you're not going to be in the middle of the molecule. Duh. Lowest electronegativity is always going to be the central atom. Typically, that's going to be carbon. Where you want to start is to find the total number of electrons in your model. Okay, you do that by adding up the valence electrons that each of the numbers has. Remember, you can tell the number of valence electrons by the group number. If it is an ion, if it's negative, that means it has more electrons. Gain electrons become negative. Okay, so you would add some extra electrons. If it's a positively charged ion, you would subtract some electrons. You always start with single bonds, okay, or sigma bonds between each pair. Look at the bonds you use, subtract to see how many electrons you're still working with, and you start placing lone pairs on each terminal one until you satisfy the octet rule. If you have any left over, you put them on the middle atom. If you don't have enough, then you move them into bonding ones. Some atoms in this class will have more than 8 electrons around them. It's okay, It'll be okay. If it's not yet surrounded by 4 electron pairs, you just convert those lone pairs and you move them into form double or triple or pi bonds. But not all elements are going to form pi bonds. The ones that typically do is carbon, nitrogen, oxygen, phosphorus, and sulfur. Another tip that can be handy to remember is honk, 1, 2, 3, 4. Okay, again, honk, 1, 2, 3, 4. That means that hydrogen forms 1 bond, oxygen forms 2, nitrogen 3, and carbon 4. So let's do some practice. We had already done HF, so I'm going to go ahead and write that. Hydrogen forms 1, fluorine has 7 valence electrons. And then you can always check the number of electrons. Hydrogen has 1 valence electron. Fluorine is in group 17, so it has 7 for a total of 8 electrons. In our model here, we have 2, 4, 6, 8 total electrons. Okay. Nitrogen has 5, so that's going to be 10 total electrons. And if you remember honk, 1, 2, 3, 4, you know that nitrogen likes to form 3 bonds. So nitrogen triple bonded to nitrogen, so there's 6 electrons used so far. We have 10, so we're going to put 1 lone pair on each of them. Okay. What about nitrogen and 3 hydrogens? Nitrogen has 5. Okay, hydrogen each has 1, so that's 3 more, so we have 8 total electrons there. Let's put our nitrogen in the middle. Hydrogen, hydrogen, hydrogen. There's 6 of our electrons so far. Okay, remember each line is 2 electrons. We have 2 more. Hydrogen can't have lone pairs, so we put it on the nitrogen. Okay, go ahead and try the next 2 on your own, and then give this one a go. Note it is an ion, but then we'll try it together. Okay, so go ahead and check your CH4, aka methane, and your carbon tetrafluoride, okay, CF4. Make sure you didn't forget the lone pairs on the fluorine. And then we're going to look at the ion, okay? So make sure you have all of these right, and let's look at that ion. Okay, let's start by figuring out how many electrons we have there. Nitrogen typically has 5 valence electrons. Oxygen has 6. And then it's a positive ion. Okay, so positive means that it's lost some electrons. It's positive 1, so we minus out 1. So we should have a total of 10 electrons there. Okay, so let's go ahead and start and see what happens. Okay, we got nitrogen. We'll start with just a single bond to oxygen. Okay, so there's 2 of our electrons. We have 8 more. So let's see what happens if I go 2, 4, 6, 8. Okay, so there's my 10 electrons. However, here nobody has an octet. Nobody. Okay, so I need to make this so that at least one of them has its octet, preferably both of them. So what I'm going to do is I'm going to take one of these lone pairs from nitrogen and change it into a bonding orbital. And that's cool because now oxygen has 8 electrons around it. 2, 4, 6, 8. But nitrogen doesn't. Nitrogen only has 6. So I'm going to take one from the oxygen and make it a bond. Okay. Now let's see where we're at. Do we have our 10 electrons? We have 2, 4, 6, 8, and 10. So yes, we have all of our electrons there. And you can tell that there's a positive charge on this because oxygen, okay, or actually we'll talk about that when we get to formal charge. But this would be the correct Lewis structure for an NO+, or I think it's called a nitrogen oxide ion. Okay. Now let's look at some Lewis structures that violate the octet rule, because we are going to be doing exceptions in this class. We have PCl5. Phosphorus has 5 valence electrons, so it will often form 5 bonds. So we put the phosphorus in the middle, and then let's just put our chlorines. And then don't forget all the lone pairs on chlorine. Boom, done. That's it. Yes, the phosphorus has 10 electrons around it. What are you going to do? Okay. Xenon is another one. Xenon doesn't care. It'll be like, I'll bond whatever. The structure for XeO3, a common one, is Xe. Oxygen likes to form 2 bonds. And actually, let's go ahead and see how many electrons we're supposed to have in this molecule. Xe is a noble gas, so it has 8. The oxygens each have 6, so 6 times 3 is 18. So we should have 26 total electrons. Okay, right now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 22, 24. Okay, all the oxygens are happy, but I still have 2 more electrons. They're going to go on the xenon. Okay, and that is okay. Xenon is in group period 5, so it can handle quite a few electron pairs around it. Okay, and if you count each bond as only one of the electrons belonging to xenon, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, and that's fine. Beryllium is another one. Beryllium is only in the second row. Okay, so beryllium only has 2 valence electrons. So BeCl3, go ahead and try it. Did you get this? Or Cl2, sorry. And that's it. That's what beryllium chloride looks like. Because beryllium doesn't have an octet. Okay? It doesn't. It only has 3 electrons. So it's perfectly happy with just 2 in its outermost shell. Now there's one more step to the Lewis structures, one more thing that can help us figure out the Lewis structure, and that's formal charge. So let's talk about formal charge. What formal charge is, ooh, there's a typo there, is the difference between the number of valence electrons on the free atoms, okay, so the atoms just as they are on the periodic table unbonded, and the number of electrons assigned to the atom in the molecule. When you have smaller formal charges, that's going to be a more favorable arrangement of the atoms. And anytime you have negative formal charges, that should be on the more electronegative element. Okay, this will make more sense once we do some examples. So, let's go ahead. Oh, the rules for determining formal charge is that electrons within a lone pair, they just belong to that atom, okay? You count them. In each bond, you count one of the electrons as belonging to that atom. And the sum of the formal charges must be 0 if it's a neutral molecule, but if it's one of those polyatomic ions, the formal charge should be equal to the charge. So right here I have 2 possible structures for carbon dioxide. They each contain the right number of total valence electrons, but which one is correct and why? we know that it's this one, okay? You probably recognize that Lewis structure. And this is because if you look at this, oxygen normally has 6 valence electrons, and in this Lewis structure, it has 2, 4, 5, 6. 6 electrons assigned to it for a formal charge of 0. Carbon normally has 4. It has half of all the bonds. It has 4 bonds around it, so 4 electrons assigned to it. That's a formal charge of 0. And this oxygen is just like the other, so that's a formal charge of 0. All 0 formal charges, good structure. Where in this one, although they still add up to 0, we have a -1 and a +1 on the 2 different oxygens. And while that's possible, it's not ideal. It's not going to be the most favorable structure. These electrons here are going to want to spread out. Okay? So let's look at another example. Okay? We're going to look at the thiocyanate ion, SCN. And it is an ion, so it's minus. Let's figure out its structure first. Sulfur has 6 valence electrons. Carbon has 4. Nitrogen has 5. It has a negative charge, so that's 1 more electron added to it. Okay, so we have 16 total electrons. We'll start with our carbon in the middle, connect it to nitrogen, and connect it to sulfur. Okay. Then that's 4 electrons so far. We have 12 more. We know carbon likes to make 4 bonds, and we know nitrogen likes to make 3. So let's go ahead and just do that and see what happens. So then we would have these charges over here and these over here. Check my counts. 2, 4, 6, 8, 10, 12, 14, 16. Okay. So we're going to go ahead and figure out the formal charges for this structure. There are other ways to draw this, and we would have to do the formal charges for all of them to figure out which is the most favorable. We'll do an example like that next. So like I said, let's fill out this chart to check. Sulfur normally has 6 valence electrons. Carbon has 4, and nitrogen has 5. In this structure, the sulfur has 2, 4, 6 lone pair electrons around it. Okay. The carbon has 0. There aren't any lone pairs on carbon. And the nitrogen has 2. Then we need to go for the shared electrons. Sulfur has 1 pair on it, so that's 2 electrons. But remember, we only count half of them, so we're going to count it as 1. Carbon has 8 electrons around it, 2 in each bond, so remember we're going to count it as 4. And nitrogen has 6, so we count it as 3. So then we can figure out the formal charges by just subtracting that. The sulfur is going to be 6 minus 6 minus 1 for a total of -1. 4 minus 0 minus 4, 0. 5 minus 2 minus 3, 0. Okay. So that looks pretty good. And look at the sum of the negative charge is 0 plus -1 is -1, and that is the charge on the ion. So that's a way we can know we got it right. Okay, let's talk about xenon O3. Let's do one more example. Give possible Lewis structure for XeO3, an explosive compound of xenon. Which Lewis structure would be most appropriate due to formal charges? So, XeO3, let's first draw the one that we did before. We had the Xe double bonded to all of the oxygens. And it had a lone pair there. But what if we had some single bonds? Let's go ahead and try some single bonds. I'm going to do another one where I'm going to take one of these, and I'm going to move it to a single bond. So oxygen, we'll say that one's double bonded, and then we have one over here that's just single bonded. Note, I'm just moving them from bonding to non-bonding. I am not changing the number of total electrons in the molecule. And then let's do one more, which has 2 single bonds. And actually, I'm going to fix this. So I want to figure out my formal charges. First, let's figure out the formal charge for those double bonded oxygens. Oxygen typically has 6 valence electrons, and in this one it has 1, 2, 3, 4, half of the bonding, so 3, 4, 5, 6, so minus 6. So that means the formal charge on the double bonded oxygens is 0, okay? And it's going to be that way for all of the double bonded oxygens. So I'm going to go through and add those zeros in. Okay. What about the, oops. That one is also a double bonded oxygen, so its formal charge is 0. What about that xenon? Okay. In this one, I'll figure out xenon normally has 8 valence electrons, and then it has 1, 2, 3, 4, 5, 6, 7, 8. So this xenon also has a formal charge of 0. Okay. What about this xenon over here? Because this xenon is bonded differently, so it's going to have a different formal charge. We have 8 minus 1, 2, 3, 4, 5, 6, 7. So minus 7. So this xenon has a formal charge of negative 1. Okay. Which means this xenon, okay, which has 8 minus 1, 2, 3, 4, 5, 6, must have a formal charge of negative 2. Okay. What about those single bonded oxygens? Well, oxygen normally has 6 valence electrons, and we minus 1, 2, 3, 4, 5, 6, 7, minus 7. So, whoopsies. I messed up. This should be 8 minus 7 is 1, not negative 1, positive 1, which means this one is definitely positive 2, 8 minus 6. Okay, while this oxygen is going to be negative 1. So that means these oxygens are also negative 1. So you can see in all of these, the sum of the formal charges is still 0 because it's a neutral atom. The most favorable one is going to be the ones with the lowest formal charges. So it would be this one right here, where all the formal charges are equal to 0. Okay, so I want to show you guys that. Oh. Okay, cool. Okay, cool.